All right, let's dive into one of the wildest, most mind-bending ideas in all of physics, quantum tunneling. Seriously, this is a concept that kind of flips our everyday intuition on its head and makes the impossible seem, well, maybe just a little bit possible. So let's get right into it. Just think about that for a second. What if you could run straight at a solid brick wall, and instead of, a very painful crash, you just popped out on the other side? In our world, that is pure science fiction, right? But what if I told you that on the tiniest, most fundamental level, this kind of thing is happening all the time? And this is the absolute heart of what we're talking about. In our normal classical world, if you throw a tennis ball at a wall, it's going to bounce off 100% of the time. It's just impossible for it to go through. But in the weird world of quantum mechanics, the rules are totally different. For a teeny tiny particle like an electron, passing through a barrier it shouldn't be able to cross, well, it's not impossible, it's just really, really improbable. So, what do we call this seemingly magical ability? Well, it's got a name, and it happens to be one of the absolute cornerstones of modern physics. Okay, so here's the textbook definition. Quantum tunneling is what happens when a particle gets through an energy barrier that, according to all the rules of classical physics, it just doesn't have enough energy to get over. It's kind of like trying to roll a car over a huge mountain, but you only have enough gas to get a quarter of the way up. And yet, somehow, the car just appears on the other side anyway. How? So how on earth does this actually work? Well, the secret isn't some kind of hidden force or a magic trick. It's actually baked into the fundamental identity of what a particle is. See, it's not just a little ball, it's also something else entirely. The whole breakthrough really started back in the 1920s. Physicists like Louis de Broglie had this revolutionary idea that every single particle, we're talking electrons, protons, everything, also behaves like a wave. And that's not just a neat analogy, it's a fundamental truth about how matter works. But wait, this wave isn't like a wave in the ocean, it's a wave of probability. Think of it like this. The wave map tells you the chances of finding the particle at any given spot. Where the wave is highest, that's where the particle is most likely to be. But its location isn't a sure thing. It's kind of smeared out across space. So here's how it plays out. As this probability wave for the particle hits a barrier, most of it bounces right off, just like you'd expect. But, and this is the crazy part, a tiny little bit of that wave actually leaks into the barrier. As it goes through, the wave gets weaker and weaker. But if the barrier is thin enough, a tiny, faint bit of that wave can make it all the way to the other side. So here's the kicker. If there's even a tiny, non-zero piece of that probability wave on the far side of the wall, then there was a non-zero probability that, poof, the particle will suddenly be found there. It didn't smash through the barrier, it just took a probabilistic shortcut. This isn't breaking the rules. This is one of the fundamental rules of how our universe is put together. Now, you might be thinking, okay, that's a cool but very weird, very abstract theory for microscopic stuff. But it's not. This impossible shortcut is actually responsible for some of the most basic processes in nature and, believe it or not, some of our most advanced technology. I mean, just look at this list. It's everywhere. From how radioactive atoms decay to the super fast electronics in our computers. We can even see individual atoms using special microscopes. And that's only possible because of quantum tunneling. But let's just zoom in on two really amazing examples. Yup, you heard that right. The sun and every single star you see in the night sky is basically a giant nuclear furnace powered by this effect. Down in the sun's core, the protons don't actually have enough energy to push past their own repulsion and fuse together. Classically, it shouldn't happen. But thanks to quantum tunneling, they can just tunnel past that energy barrier, fuse, and release the incredible amount of energy that lights up our entire solar system. Now let's bring it from the cosmic scale all the way down to the device in your hand. Every single time you save a photo to your phone or plug in a USB drive, you are using quantum tunneling. Flash memory works by pushing electrons through a super thin insulating wall to trap them, and that's how it stores a bit of data. And the only way those electrons can get through that wall? By tunneling. So it's pretty clear tunneling is absolutely essential to our world. But as we keep pushing the limits, making our technologies smaller and smaller, its role is getting even more complicated and even more important. Because it's a double-edged sword. On one hand, tunneling is becoming a huge headache for engineers. As the components in computer chips get microscopically small, the insulating barriers are now so thin that electrons just tunnel right through them when they're not supposed to, causing leaks and wasting battery life. But on the other hand, learning to control this exact same effect is the key to the next wave of technology, from the insane power of quantum computers to super efficient electronics. And that kind of leaves us with a pretty cool thought to chew on. Quantum tunneling really shows us that the universe plays by a set of rules that are way stranger and way more flexible than we ever could have imagined. It forces us to rethink that line we draw between what's truly impossible and what's just really, really, really unlikely. So you have to wonder, what other barriers are out there just waiting for us to tunnel through?